It depends on the geometry of the shaft and the nut.
And what I mean by that is when you put a high lead version on it, it's very easy to push up
So this is back drivable.
on the nut and back drive it out. Again, you can see how smooth and quiet the lead screw is.
But the one that is not back drivable, no matter how much you put the weight on it, it will not rotate. And it does not depend on the friction. I know, hard to believe, but it does not depend on the friction. It depends on the geometry.
Lead screw has definite advantages for many applications. It's smooth, quiet, clean, self-lubricating, corrosion resistance. So again, properly designed, a lead screw can be a very good product in many applications.
So the nut itself often is made out of plastic bearings. So you can make plastic nuts. Like from Egus, they make these, and it's very quiet, self-lubricating, no maintenance. So lead screw can be pretty applicable in many ways.
So some of these for lead screw itself.
Yeah, we're talking lead screw, not most. So let's see if we have more of the applications. This is a comparison of linear motion.
Ball screw-driven applications are well known for having high efficiency and decent accuracy, but there are acceleration limits that dynamic possibilities.
Okay.
In many applications, linear motors have an advantage over other drive systems. Discover the strengths and weaknesses of linear motors and 3 related techniques to identify what the best solution for your application will be. For the belt drive application,
I want to show you something like from a real world. So that's the rail. So you see that these lead screw applications, you do have a mechanical rail to sustain the weight, because you don't want the lead screw to actually be bent, right? So you have a strong, stiff rail system on the bottom to sustain the weight. So the job of the lead screw is simply to move it in the axial motion. Let's see if we have more. Installation. I want you to see it in a more like an automation context. Some of these lead can be very aggressive. So you see the angle, and this comes down to the calculation we'll do in the second session. And one rotation of this can be very fast. I saw this. I'll find it someday. There is a demonstration of a cup of water flying on this linear motion very fast, but it doesn't spill the water because the control is very good. Yeah. Okay. It's a good time for a break. Let's take 10 minutes and then come back for the calculation problem.
dosen-dosen itu sama sekali. Ya. Tapi nggak ada buat gaji bos. Iya. Kalau biasa. Rasanya itu dari awal masuk dari itu. Buat diapain lagi dong? Bukannya makin banyak orang beli makin bagus kan? Oke, gimana sih? Yang mau banyak lagi, nggak bayar. Oh, curi. Woi, my phone. Ini insurance. Kalau enggak, saya masukin ke partner saya. Gila, itu disuntik minyak ya? Sawit, sawit ya, minyak sawit. Kalau jumlah yang bikin tanda tangan petition berapa kalau 50% agak sulit sih. Yang dari yang siap biasanya 50 2/3.
Kenapa ke gua semua?
Karena lu yang udah WA-an. Pagi. Coba kita tanya ya. Kalau dari batch 24 yang memberangkat ke Jerman sekian persennya nanda tangan petisi bahwa nggak mau apa?
Who has a piece of scissors and a paper? Ada yang punya gunting nggak?
Teman-temannya Fendi. Ini apa maksudnya di situ.
Ini yang di belakang bukan sih, bukan yang di office yang
Ya tapi kan satu itu kan. Pasti kalau makan siang bareng itu Nah, ya udah, sebelumnya baru. Kalau kita ngadain
Yay.
dua per tiga yang mau berangkat ke Jerman, dia kita doang. Batch atas tuh udah berapa? Biar yang ke sana bayar SPP, SGU-nya nggak full. Angkatannya Pak Seta masih.
bentar dulu ya Ian ya, gue fokus ke sini.
Iya, kata dia 3 sampai 4 juta. Bukan turis ya.
Portion.
Bahasanya cek.
Let's have the ladies do this.
Pop quiz. Pop quiz. Bisa pakai itu lipat, rock, rapi.
That's a great idea. Okay, I found a few good videos just for you to get a feel of these things. This is the comparison between, well, this is just a linear belt drive. Here's a comparison between a ball screw and a belt driven. This is belt driven, so that's the kind of speed you can see. This is the kind of speed you see with ball screws, even though there are fast ball screws too. I cannot find the videos that I want, but if you go to trade shows, which, like if you take my course on automation machine design, I usually take you to an automation trade show in November, I think. Good show to go to. Okay, that's for later. For now, let's go into the calculations. Here is a comparison between lead screw and ball screws. Lead screws are quiet, lower efficiency, higher efficiency. I guess the downside of ball screw is mainly noisy, but also lubrication. You'll have to lubricate it well. Unicycle is a bit more limited on lead screws. It can be self-lubricating. This definitely needs lubrication. For ball
Which one has better capabilities?
ball screws. Yeah. So generally speaking, ball screws are better for applications that require smooth motion, efficiency, accuracy, precision, and prolonged continuous high-speed motion. Traditional lead screws are more suitable for simple applications. speed, accuracy, precision are not as critical. Okay? Now, today we're going to look into the calculations of lead screws. Now, lead screws are typically Acme threads. Older power screws might be a square thread, but this is called an Acme thread. Okay? ACME. Okay, ACME. And it has a specified angle of 29 degrees. That's why. So half of it will be 14.5. So the angle between the vertical to this angle will be 14.5, but this entire angle is 29. And that's standard for Acme thread. This is what you see in most lead screws. So we're going to do some mechanics of power screw. And in any lead screw, you can have a single start, double start, and triple start. And this is the difference between the pitch and the lead. Now, it's very hard to imagine this unless you actually see it in working, but we don't have such prototype. So a single start, the lead is the same as the pitch. Lead is how much you travel in one rotation. Okay? So the lead is not necessarily the same as the pitch. The lead of a lead screw is how much linear travel in one rotation. Okay? The pitch is basically the distance from one peak or from peak to peak. From, okay, one peak to the next one. So it's a mechanical property here. Basically, the pitch, the green, is the distance from one mountain to the next mountain, okay? Just that distance, that's it. But the lead is how much you travel in one rotation. And believe it or not, it doesn't have to be the same. So in a single start thread, the lead is the same as the pitch. So one rotation is one pitch. Okay? So in a single start, this is the pitch, right? One rotation is one pitch. Simple. A double start, one rotation, you travel two pitch. In a triple start, there are also 4 starts. In one rotation, you actually travel 3 times the pitch. So how can this be? In order to show that, I'll have to do a physical demonstration. So, a single start is like having a single thread. I'll just use this. You have a single thread. I'll just color it. A single thread, wrap around it like this. Okay? Any typical bolt is like this. Now a double thread, you actually have 2, and I'll draw it a different color. It's not that different, but black and blue, 2 of them prepped like this. Okay? And like that. And so if you trace the thread, like put your fingernail on it, you'll end up skipping one. Because there is another thread, the blue one, that if you trace it with your fingernail, you end up here. And you can guess it, the triple start will be having 3 of them. And I need a longer piece of pen here, but something like that. Okay?
Yep.
So, sorry about that.
Sama itu ukurannya. Micro water.
I don't know.
What are
maybe.
these?
Okay, so this, I closed the blank. Okay, see that? So, because of this, you can imagine, because if you trace your fingernail down the red line, you'll show up here. So can you see that one rotation, you'll go 3 pitch. So the angle will also be more aggressive. But you're not changing the pitch, you're changing the lead. The pitch is still the same. So because of this, you'll have lead and pitch. And lead is different than pitch. So for a single start, your lead, L, will be the same as the pitch. And for a double start, and for a 3 start, and for a 4 start. I think it only goes up to 4, otherwise it's too aggressive. Okay? So that is an important part of the equation when you put in L. So it comes down to just these 2 equations. There's a third one for the color, but L, this is an L, not an I. L is the lead. Okay? And one more formula here, the self-locking condition is calculated this way. And you'll see it once we go through the equations. The application for a self-locking will be like a jack, like a car being lifted. Obviously, you don't want the weight of the car to drop the carrier, even though you can maybe fight that with your motor, but you don't want your motor working all the time to sustain it. 1, electrical consumption, you'll burn your motor. 2nd, safety. You don't want. Okay, so jack will be an application for you do want self-locking. Back drivable is an application maybe in robotics. You know how the robotic hands, sometimes you want to be able to move the robotic hands, and actually the motor, you move the motor when you physically move the hand for teaching mode. Teaching mode is when you move the hand of the robot to the places that you want, and it'll go there after the teaching mode. So robotics is one area. Many times in automation, you also want to prevent pinching, safety. Okay, you want to be able to move it. If you stop the machine, you want to be able to move the mechanics. Okay, so this is self-locking condition that you can actually calculate. Finally, you can calculate the efficiency of the power screw with this formula. I'll show it in the example. Okay. I think I pull it out. Okay, hold on. All right. So this is our exercise. We have an Acme thread power screw. We have a major diameter, 32 millimeters, and a pitch of 44 millimeters with a double thread. So for a double thread, what's the lead and pitch relationship?
The lead is twice.
The lead is twice the pitch. Okay. Now, there are some variables that I need to define here. We are given the data for the friction coefficient, both on the lead and on the collar is 0.1. This is the diameter of the collar. And what I mean by the collar is that if this is the lead screw, it has an axial reaction, right? And the axial reaction has to be sustained by a bearing that can rotate while taking an axial load. And this is called the collar. Okay? So the friction of the collar will come into play also. The vertical load is 6.4 Newton. So we are a lifting situation here. So this is the collar. This is the carrier. Okay? We have a vertical load basically of 6.4 kilonewton. Find the torque. So this is connected with a motor. The motor rotates, lifting it up. So the torque to raise, to lower, which we'll do torque lower later on. And then find the efficiency and find if this power screw is self-locking. Okay? Now, the torque to raise is a combination of the torque to raise, TR, plus TC. Okay, so let's calculate each one. So we have TR. Now notice that you have two formulas. This is for a square thread. This is for an Acme thread. So pick the right one. Okay? Notice with an Acme thread, you have the alpha. So for Acme thread, you have the secant alpha. That's what you have to notice. And alpha is always 14.5 degrees for Acme thread. What is secant? 1 over sine, cosine, tangent. You don't sound confident. 1 over cosine. Okay. So the formula is this one that we picked. We have F Bm. I won't rewrite. Okay. So F, I'll just define here. Bm is the mean diameter. In this case, we have a major diameter of 32. So if you look at the threads, right? This is 32. And we have a pitch with the pitch is 4 millimeters. So this is the mean diameter that we want. So it's slightly smaller than the major diameter. And you basically do 32 minus the pitch divided by 2. Okay? So we have F is the load. I don't think I have enough room for this. L is the lead. Find room for this. Okay, so L, the lead, this is a double start, so twice the pitch. Okay, so L is 0.008, everything is in meters. Pi times the friction coefficient, the mean diameter, secant of 14.5. Pi 0.03, the mean diameter, minus 0.1 times 0.008, secant of 14.5. So that's the torque to raise it without the collar torque. We'll discuss that soon. So we have 96 this is 17.88 Newton meter. Okay, any questions so far on these numbers?
Sir, what's the C stand for, sir? It's like F, FEC.
Which C?
Oh, DC. Torque.
Torque of the collar.
And TR is to raise.
Is the torque to raise on the lead screw.
Lead screw. So lead screw plus collar is
Right, so the torque to rotate is, you know, we need the TR here and we need the TC here. It's a combination, it's a summation of both. Okay? So we have the TC is F 6400 times FC, which is the friction coefficient of the collar, 0.1, and the diameter of the collar, 40, divided by 2, and that is equal to 12.8 Newton meter. And this is always there, right? Regardless whether you want to raise it or lower it, this will always be there. This is the torque to lower it. So the collar is a friction that has to be there. So a combination, the torque, total torque to raise is equal to TR plus TC, which is 30.69 Newton meter. Okay, any questions so far on the torque to raise? This is probably a good explanation of the mean diameter. So this is the pitch, right? I know this for square thread, but acme thread is similar. This is the pitch. So the height of this tooth is P over 2, but we want the mean diameter here. Again, this is the major diameter. What we want is in the middle of this. Mean diameter. Because this is the compact of the lead nut and the lead screw. And the mean diameter will be the major diameter. So dm will be major diameter minus pitch over 4. P over 2 is P over 4, right? Minus pitch over 4 on the other side. Because this is P over 2. So this is P over 4. Right? So is the major diameter minus pitch over 2. Therefore, the mean diameter is 32 minus 4 over 2 is 30. Any questions on any of the terms? Friction coefficient, right? Alpha for acme is 14.5. Okay?
So the small F is like friction for the, one is like for collar, one is for the lead screw.
Yes, which happens to be the same. The friction and the collar friction is both 0.1. Okay, now we find the efficiency. E is 6,400 times the lead, which is twice the pitch, divided by 2 pi the torque to raise it. Now this is already a simplification of the original formula, basically TO divided by TR. The question becomes, what is the torque required Okay? So, because of the friction, the torque required to rotate the screw is less than, with the load, is less than is necessary to overcome the collar friction alone. So the overall efficiency is defined by the TO over TR. Now, we check for less self-lock. It's self-locking, right? We see that the TL has a term here, and this term is basically what we check. So if you want to check for self-lock, that's what we check. If this term is greater than the lead or not. Because this term, pi, friction, coefficient, mean diameter, secant alpha, minus L. So if this is greater, what happens to this term? Positive. If this is less than L, what happens to this term? It's negative. A negative TL does not make sense, right? If the torque to lower is negative, then it means no torque required. Right? Does that make sense? If the torque to lower is positive, then in order to lower it, you need to apply torque. But if the torque to lower it is negative, then it is self-locking. So if we compare this, pi times 0.1 times 0.03 secant of 14.5 is equal to 0.0097, which is greater than 0.008, which is the lead. So yes, it is self-locking. Okay? And if you check, obviously, this is 0.0097 minus 0.08, so this is a positive, so the entire term is positive. So you need torque to lower it. So it's self-locking. Yeah.
So the TR there and the TR there is different. The TR in the efficiency.
It's the same.
But we can use the TR 17.8.
Oh, right. With the collar. It's the TR with the collar. I know, it's kind of confusing. I every year I saw this and I want to revise my keep forgetting. So here you put in the TR that is already a summation of the TR plus TC. Note to self again. Including collar. When you have the quiz, I'll have it revised. Okay, any questions about self-lock, efficiency? All right, well, just one example for inner motion. So quiz on Tuesday and
the next Tuesday.
No, baru satu.
yeah, we'll have a quiz on this. One final topic I have is springs no, two final topics is
Spring
spring and
and-
fasteners. Okay, so we have two more topics, but maybe we'll merge that in all in one quiz.
So the last quiz will be on this and springs.
Take pictures. Me first. What's your question?
The last quiz, like after the belt and jeans, will be on this and springs or just different?
I don't know yet. I think this and spring and fastener. Fastener is very simple though.
Sir,
Yeah.
is the results for the last quiz already out?
Yeah, the scores are
I'll return it on Tuesday.
next Tuesday.
This coming
Pas
Tuesday.
quiz.
Kena mental dulu.
Pas mau quiz, ngeliat quiz sebelumnya.
Terus,
Wah.
Antara mungkin semangat kalau nggak kena mental. Ya kan?
Yang kedua.
Oke,
No, only for HEVs. Oh, post quiz.
Oh, post test. Do the post test, please. Same thing.
You sleep?
This 30 minutes later anyway.
Sir, ball is more capable than lead, right, sir?
Yes.
What is
Yes.
compared to linear belt drive
Definitely more accurate. Ball screws.
ball screw is more repeatable.
Yes.
Hari Senin langsung balik kan? Sekarang ganti.
Senin tuh nggak ada apa ya? Kayaknya ada soal.
Senin yang ininya ada Jerman, terus HEV nggak ada apa-apa.
Kita ini Senin nggak ada.
HEV
Iya,
nggak
ada
di
di
apa gitu?
Jadi
HEV dia nggak ada Jerman.
Oh.
You don't have German on Monday, so you don't come on Monday.
Oh wait, the Pak Boris when ya? Pak Boris Tuesday or
Apaan? Wednesday.
oh, Wednesday.
Solo class on Monday.
Rabu depan grup 1-2. Rabu depannya lagi 3-4.
Tadinya telat juga. Dia berbaik tesis.
Apaan?
Tadinya telat.
Hari ini. Semangat. Telat sampai jam berapa? Dia bilang 30.
Okay, it's okay. Rather be sorry than safe.
Gue balik sekarang. Gak ada yang mendukung Anda.
Tapi kanan.